Hi, see all of this math on the board behind me? Besides being math, what do all these ideas and concepts have in common? At first glance, not much. These algorithms or processes are taught in different grades, and they're usually presented as unrelated topics. But there is a common structural theme running through them that can make it easier for students to remember and understand the whys and hows of the algorithms taught for these math concepts. I believe these ideas are all connected by one underlying structure: counting. Hi, I'm Calvin. I'm a retired high school math and science teacher and elementary principal with over 40 years of experience. I am not a YouTube pro, but I would like K-12 math teachers to take a few minutes to consider why so many students struggle with understanding and making meaning in mathematics, and what we can do about it. If we envision mathematics as a large tree, we usually show students the ends of the branches, like the examples on this board, as disconnected topics and algorithms. Then we wonder why so many of them can't remember it all. I believe we need to get them to know and understand the trunk, the counting core, and show them how the branches are connected back to that counting core so they can understand how these concepts are all interrelated. How might it look if we used a coherent framework based on counting to interconnect these ideas and others as students progressed from kindergarten to grade 12? Mathematics would make more sense, it would feel more organized, and more students would be able to better understand it, remember it, and build upon it. I'll show you what I mean. Let's go through the examples on the board. So in the top left corner here, we would have what kindergarten and grade 1 teachers would do in their classrooms. They would have these dice faces, and they might ask a question like, how many cats are there? So the kids in their head have to say, okay, these are the 3 cats, these are not, so 1, 2, 3 cats. Or if we said, how many dogs? And then we say, okay, 1, 2. Doesn't matter that they're over there and over there apart. We still count them together because they fit the description. If you're doing a little bit of science, you could say something like, how many mammals are there? Now they would say 1, 2, 3, 4, 5. You could count legs, etc., but it's counting. 8 plus 6. Now it's still counting. They're adding ones, 8 ones plus 6 ones, but we're wanting them to do it faster. So if we bring down some number line sections here, the idea is we want them adding 8 ones with 6 ones, and they see that it lands at 14. Okay, and the idea here is you can teach all sorts of things, like we're taking 2 from the 6 and making 10, and then the remaining 4, and we could show tiles for all those things as well. All right. The idea, though, is that they're using the adding as a shortcut for counting. 3 plus 3 plus 3. Repeated addition, we demonstrate as follows. We have number strips. We can say, okay, there's 1 3. There's 2 3s. There's 3 3s. We land at 9. If you're introducing multiplication, then you can start saying things like, okay, we're going to do skip counting. They can actually see the chunks that you're jumping by now. So 3, 6, 9, and then you can also carry on and say, okay, there's 1 3, 2 3, 3 3s. So you're getting into multiplication. 1 3 is 3, 2 3s is 6, 3 3s is 9. Without even saying the word division, if you wanted to introduce the idea, you can ask the question of how many times can I remove a 3 from 9? I can remove 1 3, I can remove 2 3s, I can remove 3 3s from the 9. 4 times negative 2. Many students struggle with the integer rules of positive times negative makes negative, etc. And many teachers struggle with trying to explain that to kids as well. So 4 times negative 2 is literally you're counting 4 negative 2's. You have 4 of these things. And here are the negative 2 tiles. So I bring down a negative section of the number line. And we start placing the negative 2 tiles. There's 1 negative 2, 2 negative 2's, 3 negative 2's, 4 negative 2's, lands you at negative 8. Likewise, so a positive times a negative, That's why we're landing negative. Likewise, we can also demonstrate to the students now, -8 divided by -2 is asking how many times can I remove a -2 from -8. I can remove one -2, I can remove 2 of them, I can remove 3 of them, I can remove 4 of them. That's why -8 divided by -2 is +4. We teach fraction addition, and the idea is that a lot of times we dive right into the algorithm of finding common denominators, and we start giving them rules to memorize to add together fractions, as opposed to let's approach it from a counting perspective. What is this saying? We have one of these things called halves plus 2 of these things called thirds. This is what I mean. If the hexagon is a whole, then 1/2 means one of these things. 2/3 means I have 2 of these things. The rhombuses are a third of the hexagon. So when we're going to look at the counting, one of the, oh wait a minute, these are different things. They're not alike, just like the cats and the dogs. I can't count them together. However, I can see that if I put the 2/3 and the 1/2 together, it should make one whole plus one more little triangle. So here's what we know the answer should be that. Here's what we do. We replace the half with these 3 triangles. That's what you're doing when you're making a common denominator. Multiplying by 3, they're smaller parts, and you have 3 times as many. We're making change. Each of these blue rhombuses get replaced by these green triangles, the 6. And now, because they can see that the shapes are the same, these are the same types of shapes. I can count those together. 1, 2, 3, 4, 5, 6, 7 of these things called sixths. And the important thing is the bottom number doesn't change because it's 3/6 plus 4/6. We're counting. That's why the 6 stays 6. When you're counting up here, 1, 2, 3 cats, the cats are still cats. Bed mass. A lot of teachers and students struggle with understanding why the rules are the way they are. And in many cases, I think teachers kind of just default to, well, those are the rules, we have to follow them. But the rules are actually an interpretation of the actual math. So let's take a look at what this is saying. There's a 3. There's and 4 5s. And 3 2s. When you look at it like this, you say, okay, well, what is it we have 3 of here? We have 3 1s. The job of this 4 is telling us that we have 4 of these things that are called 5s. 1s and 5s are not the same thing, just like cats and dogs are not the same thing. That's why we can't add the 3 and the 4 yet. However, we can say, okay, well, look, we have 3 1s. We're going to make change. 4 5s is worth 20. 3 2s is worth 6. Now they're all 1s. That's why it equals 29. It's all in the counting. It structures the whole thing for us. Up here, the algebra. We have 3 of these things that are called x squareds. We have a 2x. And we have a 1. And then over here we have another x squared. We have 5 of these things that are called x's. And we have 2 1s. This question is structurally identical to this question. We're only counting. It doesn't matter that a dog is over here and a dog is over here, just like it doesn't matter that an x squared's over here and some x squareds are over here. How many of them do we have altogether? There's 1, 2, 3, 4 of these things that are called x squareds. But because we're just counting, that's why they're still x squareds. We don't add the exponents because we have 3 of them and 1 more over here. 1, 2, 3, 4, 5, 6, 7 of these things that are called x's, but there's still x's plus 3. So there's the structure on all of this mathematics on how counting can explain the algorithms for all of it. These are just a few examples of how counting connects together many topics in math. I believe this counting framework can be used to organize and make sense of much of the mathematics we teach from kindergarten to grade 12. If this video makes sense to you, or it helped you to see relationships between mathematical concepts that you didn't see before, like this video, subscribe to the channel, share it with your teacher colleagues. Post a comment below or email me if you have any questions or thoughts you'd like to share. Over time, I'll be posting more videos showing how this framework can be used in individual classrooms, or better yet, as part of a whole school journey and approach to supporting students' mathematics learning. That's why I've developed and named this framework, Let's Count on Math. Find the counting, find the meaning.